Okay, question about a problem for homework. We have this, P is L, identified with L, but how does R relate to K? Okay, just two different forms of a logistic equation. And it just comes down to setting these equal, and I think I forgot to put the prime, at least you guys are telling me I did, and I must have, on this P, which made it really confusing, okay? So, okay, now we'll talk about motion with drag force. There are two cases that we're going to consider, and they're intermediate cases, okay? Now, drag proportional to V, where you're, say, moving through the water with a nice laminar flow and not a lot of turbulence, or drag proportional to V squared, which is what happens when you start getting turbulence, okay? And these aren't exact proportions, but they're pretty indicative and they work pretty well. Okay. So if drag is proportional to V, then F net equals the applied force. If you're swimming, that's the force you exert on the water then exerts a force on you which pushes you forward. Okay? And it B minus, and it's a kappa, which is a lot like a K, and I didn't really draw a very good one there. Maybe I'll improve. This, right? So you could have this equation, or you could have this equation. And they use kappa for both of these. Okay? So using the notation in your book, I actually looked to see what the notation was. We have these two cases. Now, okay, first assume F applied is constant. Okay? Then you have either this or this, right? For the first case, you have net force, which is mass times acceleration, which is mass times the derivative with respect to time your velocity. Okay? And I'm going to go ahead and write that as dv dt. Just to be really clear that it's derivative with respect to t, because that's going to become important in the next section. Okay? And this equals I'll just abbreviate applied F app minus kappa V. So how are you going to solve that equation?
Solve it for.
I'm sorry?
Solve it for. Solve it for what?
Okay, you want to treat it as first order linear non-homogeneous? Sure you are. We're not going to.
Yeah.
We're going to treat it as separable. Okay? In part because this isn't first order linear. It's not linear. Okay? It's first order, it's not homogeneous, it's not linear. And I'm not going to be able to do that. Okay? And when I said on your homework you were treating it as separable, you're treating it as first order linear non-homogeneous, but you also be able to treat it as separable. Okay? For the logistic equation. Okay, anyhow, you have this. So what's our solution going to be? We're going to separate it. You know, we divide both sides by this, and all our v's are over here. And we easily rearrange it to dv over f applied minus kappa v debating whether I want the m over here or over there. Really doesn't matter, okay? But we could also do a kappa over m here, f applied over m, kappa over m, okay? And there are advantages of seeing it that way too. Okay, so it's real easy to integrate. You just let your u equal this whole thing. Your du is negative kappa dv, so that dv is negative 1 over kappa du. So it all comes out, okay? And over here you integrate 1 over m as a constant and all that, and you know how to do that, okay? So I'll just put an et cetera down here. So that's really an easy equation to solve if your applied force is constant, okay? If your applied force is a function of t, then the equation is no longer separable. But it is first order linear. It just has a non-homogeneous part over here, and you can then do what you want to do. Okay? So it's handy to be able to do it either way. This way is probably more straightforward when you have a constant applied force. So, assuming that this is constant, we have this. Okay? If f is a function of t, the equation is no longer separable. It is first order non-homogeneous, and depending on what function of t you have, it's maybe integrable, maybe not. Okay, when you do your integrating factor, left-hand side is automatically integrable. Right-hand side times the integrating factor maybe is, maybe isn't. T's a power function, it's pretty simple, okay? Sine or cosine, you're going to be able to integrate. It's an arctangent, you're not going to be able to integrate. Okay? So, and you understand what I'm saying, don't you? Okay? You've done this. Okay? And if you don't understand, well, I'll give you a couple, and then you'll understand. Okay? Sometimes you can integrate, sometimes you can't. You know that's the case for non-homogeneous equations. If f is a function of x, then you can't use the dv dt thing, because now you've got x, its derivative, and its second derivative, right? Okay? So those are three cases you want to keep in mind. You know how to handle all three cases if f app of x is a multiple of x, because then it just becomes a second order with constant coefficients. Okay? if f app was like proportional to x squared or the reciprocal of x squared, okay? Like for gravity, well, we'll see how to deal with that, but it's not gonna work out with anything you know at this point, okay? But if x is just if f app of x is a constant multiple of x, you can see this is going to be a second order linear, or second order linear with constant coefficients, right? Okay? Okay. So, all these cases, if I don't give you a really nasty f app, are pretty straightforward. So you'll be able to solve. Now we'll solve some and see what it tells us about different motion in different cases, but that's kind of what you have. Okay, now for the second case, the hard case, okay, you have this, okay? Now, if f app is constant, then again, it's separable. Also, if f app was a multiple of v, okay, that would still be separable. Okay? Unusual, you'd have an applied force proportional to your velocity. Okay? Unusual. You usually don't get more force as you increase velocity. Okay? Like not with a constant mass anyway. With a rocket, you can get more acceleration as your velocity increases, but that gets into rocket science. Okay? We'll talk a little bit about it, but the equations are a little bit more intractable. Okay? Okay, so you get a v over f app minus v squared minus kappa. V squared equals 1 over m dt. Now, what are you going to do with this? How are you going to integrate that? A standard technique that you learned in pre-calculus.
We're not going to do a U sub again?
Do what?
We're not going to do a U sub again?
Well, what are you going to let u equal?
Just the f app minus k.
Well, then your derivative, your du, would be negative 2 kappa v dv. You don't have a v dv, right? So you're done. I mean, that one's out the window. It won't work. Okay, so give you du equals negative 2 kappa v dv, and you ain't got no v dv, to change the variable. Okay? I mean, you would get dv equals du over negative 2 kappa v. You got a v over here, right? If you had a v dv here, then, you know, you could, then v dv would equal like du over negative 2 kappa. That'd be nice, but doesn't happen. Okay? Okay, so let's look at that integral. Okay? If we do the right thing, we can use our old friend partial fractions. Well, what do you have to do before you can use partial fractions?
Understand partial fractions.
Again?
Understand partial fractions. Yeah.
Still didn't, I really need to put this thing in. What now?
Yeah, I just said understand partial fractions. Yeah.
Well, understanding
Some more
partial
practice.
fractions,
Yeah.
it just takes a little practice. But before you can use partial fractions, you have to have two factors or more in the denominator.
Right.
So how are you going to get two factors or more in the denominator? Well, I would say, no, I can hear myself. I could say that you probably want to factor this. Okay, well, that's the factor it is a difference of two squares. Then you're going to have just a first power of v in each factor. Okay? So, well, it's starting to look familiar. I mean, not the notations. We would factor it as a difference of two squares. Okay? Square root of this minus the square root of this times the square root of this plus the square root of this. Okay? So factor probably not something that would immediately occur to you unless you had recently done a section where you'd seen this. It's not really a trick, okay? But seen this idea, right? Anytime you have a difference of two quantities here, you can try to factor as a difference of two squares. Now, depending what the power of v is, maybe that works, maybe it doesn't, but here it does. Okay? So, we need to find A and B such that A over square root of f applied minus the square root of kappa v plus b over square root of f out plus square root of kappa v equals 1 over f out minus kappa v squared. Okay? Well, do the common denominator. You're going to have a times square root of f out plus kappa v plus b times the square root of f out minus kappa v over the product of these two, which is just what? F app times F app, square root of F app times the square root of F app. This gives you F app, right? And the square root of F app times kappa V, and then negative kappa V times the square root of F app gives you 0. And then you have the square root of kappa times V times the negative square root of kappa times v, which gives you a negative kappa v squared. You want to write that out and reinforce that because it's not an uncommon technique, not an uncommon thing that you could have to do. So I'm not going to write it out in gory detail. We do the arithmetic. So this equals 1 over f hat minus kappa b squared, which tells you then that, again, skipping steps because you've just done this, I hope, with the logistic equation, you're going to get kappa v times a minus b, which is square root of kappa. And then the a plus b squared of f app identically equal to 1. We rearrange this, we have all the v terms over here, right? Because anything we multiply by v has to equal whatever the coefficient of v is over here. And there's no term over here with the coefficient of v, so a minus b has to be 0, and a plus b equals 1 over the square root of f app. So a equals b from this, and since a plus b is this, then 2a equals this, so that equals 1 over 2 square root of f app. Okay? A equals b from this one, then using that, you find that they're both equal to this. Okay? So now we have, again, our partial fractions. So the integral of a over this plus b over this, where a is 1 over 2 squared root of f out, and that's b. So I can just write the a and b, well, I can just write 1 over this, right? And then that's going to be times the integral of reciprocal of this. Okay? And we can integrate that. If we let u equal f out minus kappa b squared, we can integrate this one. And then with the plus, we can integrate this one, right? And this is going to be 1 over 2 square root of f out multiplied by this. Okay, I kind of did the substitution in my head, but I also remember how it worked out when we did the logistic equation. Okay, and then you're going to get the reciprocal of this when you do your du. Okay, And those V's aren't squared. I don't know why you wrote it down that way. But wrist got out of control or something, I don't know. You need to control that wrist. Okay. Okay. So we get this, right? And just to check it, we take the derivative of this, the derivative of the inner function, and it's not V squared, is it? The inner derivative of the inner function is kappa V, or kappa, okay? Which we then multiply by negative 1 over kappa times the reciprocal of this thing, okay, just by the chain, okay? And the kappas go away, and the negatives go away, right? So, fairly confident that we did this because we checked. And it reinforces our technique and gives us deeper insight into the technique of integration while we're at it. Okay, so we want to do that. And 2 kappa square root of f out. Okay? Which sort of bothers me, but not really. I'm checking that, checking the units of this in my head, thinking about what the units on the right-hand side are going to be, which are going to be time. And you know what? Oh yeah, it's got the mass in it. Okay, never mind. I was disturbed by something that was going to happen in the near future because I forgot that I had my mass term over on the other side. Okay. Okay, anyhow, we get the natural log of and this is, I'll just put it as T over M plus a constant. Okay? So that kappa times the square root of f out should have units of T over M. Okay? Got a square root in that f out. Kappa is going to be in newtons per. I'm still disturbed by the units. Okay? So we might have to go back and debug this. Still, you see where it's gone, right? So we get f out plus kappa v over f out minus kappa v equals a e to the 2 kappa over m 2 kappa square root of f out over m t, and the c is what gives us our a, and we've been through the details of that at least 3 or 4 times now, so I'm not going to do the details of that. What I am going to do is worry a lot about this constant, which should have units of reciprocal seconds, but I don't have the right number of kilograms. Okay? Kappa is going to have a kilogram in it. That's going to have a kilogram in it. It gives me a kilogram to 3 halves over a kilogram. I don't like that. Okay, so I'm going to turn off the camera and figure out where I might have gone wrong.